Hello, and welcome back to Linear Regression with Rstudio. Where we left off was a discussion on the R squared value. Now, in the previous recording, I didn't get a chance to talk about what Y and X are, but they are what you would think in this application. 88% of the Y in this case, should be replaced by labor hours. So 88% of the reason labor hours varies is due to the variation in X, which is cubic feet moved. This is important to me because 88% of the reason the labor hours will fluctuate from one job to another is known. Yes, there's about 10% that's not known, but I know 88% of the reason. And according to my theory, that is a lot. And I know a lot about how the fluctuation in labor hours will be dealt with by dealing with cubic feet and improving that or increasing or decreasing or working with that variable. All right, so R squared is a very valuable tool when it comes to analysis. All right, now that we've done that, we should do one more thing because if the professor wants, let me get into here, a professor wants the confidence intervals, the confidence intervals at 95%. Let's say the professor wants the confidence intervals at 95%. Not hard to do again in Rstudio. You run confident interval, CONFINT, of your regression line. And remember, in my case, my regression line is called move line 1 from the previous video. If you're just now joining me, you will have to probably watch the previous video or just catch up. Of course, I made that a hashtag. I'm going to go back now, get rid of the hashtag, which is a comment. Anytime I use a hashtag, that is a comment that I'm just writing for you guys to read. When I actually want to run the code, the line code, I will get rid of the hashtag. So confident on your regression equation, your linear model, will give you your confidence interval. And the one I care most about is the slope. What this is a 95% confidence interval for the true slope beta 1. You see, when we do regression analysis, it's typically on a sample. And so when we have a sample, this is your sample slope. Your sample slope is 0.05 roughly. And so that's your sample slope, but that's not the true population slope. We would not know the true population slope unless we had all the data values. That's what population means. Sample means we have a subset. And so if I was to give a 95% confidence interval where the true slope occurred, this would be my lower bound, about 0.04. This would be my upper bound, about 0.056. Now, why is the confidence interval important? Well, it's another tool for a significance check. If you notice, 0 is not between these values. Now, why is 0 important? Because 0, if the slope was 0, if I just think about that, if here's my scatter plot still up, if my scatter plot was pretty much roughly horizontal, that would tell me as x increases, y doesn't vary. Think about that. As x increases, y doesn't vary. And if that's true, then x and y are not really related. So in this case, because 0 is not in this interval for the slope, then we do have a significant linear relationship again. And in fact, some people think about the prediction equation right here, and when I wrote it up here, here's our prediction equation. Could they manipulate the slope to give a higher projection or a lower projection? The answer is yes. You could use the 95% confidence interval for slope, utilize these numbers, and replace them in this equation for higher and lower level predictions if one so choose. All right, so I promised you a residual analysis, and that's what we're about to approach now. I would like to do a residual analysis. So to do a residual analysis, we need to first put the residuals into a saved data file. In this case, I'm going to call it residual 1 or res1. And then I need the residuals of my map. And there it is, the residuals of my linear model. Also, I want the predicted values, and I'll call it predicted 1. Again, recall from previous videos, the reason why I'm putting 1s there are just in case Rstudio has something preloaded that I don't want to have a trouble with. That's really all the ones are about. It also could be my first example. Residual 2 would go for example 2. So right now, I took the residual values and the predicted values. All right, remember, the predicted values would be the values when I plug my x values in and see how well they did. The residuals would be the error terms. They would be the actual minus the predicted values. And now I'm going to plot the predicted versus the residuals. And of course, that plot is not helpful. I need predicted 1. Let's make sure I plot it correctly. So what we have here is predicted 1 versus residual 1. I'm not sure what this plot gave us. That was not important. This is the plot I needed. Because again, I called my residuals and residuals 1, and I called my predicted values and predicted 1. Over here is my predicted 1 versus residual 1 plot. So what am I looking for here? Well, remember, we're looking for the line check. That is, I'm looking for linearity. And so what I'm hoping for linearity is when I look at this plot, as I go straight across, there is pretty much an even scatter as I look left to right. So when I look left to right, it's a very even scatter of the residuals. What that tells me is there's nothing hidden in the residuals that I might have missed. That is, a linear regression looks appropriate. So the scatter looks roughly random, and so this check is good. All right, now linearity L, I, independence. Well, independence is more of a, are you worried about you collected your data weekly, quarterly, hourly? Could that have some impact? That is one residual affecting the prior residual? All right, is this residual affecting the previous residual? Is there any impact on one residual to the next residual? Well, the way we're going to attack the independence is I'm going to run the Durbin-Watson statistic. We will do that soon. So we're going to pause on independence for momentarily. Now, we're going to talk about the normality, the normal. And so with the normality, what I like to do in there is well, this is all about is your, I should say, are your residuals roughly normally distributed? To find this out, we will use the plot function. So again, I'm going to pause on that one and come right back to it. The only reason I'm talking about them now is because I gave you the acronym LINE, and I want to go through the acronym in order: linearity, independence, normal, and then equal variance. Some people call that the homogeneity test. So equal variance I could do in this plot. That is, I could do in this plot right here. Again, what I need to look for is, as I look left to right, is there any type of growth or decay? If the variance, because we're looking at the variance, the spread, if the spread of these dots gets wider or the spread of these dots get closer, then I have an issue with equal variance, and maybe a transformation of my data set would be something I need to do. We'll look at this in further videos down in the future. Right now, this is pretty equally spread. The spread does not grow or decrease. So I'm going to say, since the spread of the residuals is roughly even, we are good. So right now, linearity and equal variance are checked off the board. All right, again, to make sure my residuals are good and to make sure my checks are good, I have to do all 4 checks. In every type of hypothesis test, there are assumptions you have to pass. The assumptions in regression is the the line check. Linearity and equal variance have been checked. All right, so I want to continue on. I want to go back now, and I want to look at normality. So the way I would look at normality is I would plot, and in this case, let me just suspect, I would plot move line 1. And what it's going to do when I plot move line 1, our linear model, is going to bring up a bunch of individual plots. And that's why it's blinking, saying, are you ready to see the plots? So here we go. The first plot is very similar to the plot we had, fitted versus residuals. So in some respects, we didn't have to do that plot because it's right here. And as you can see, look left to right, the linearity looks good because the scatter looks roughly equal, and equivariance looks good because as I look left to right, there is no growth or decay, except for that one dot, and of course it's been labeled, maybe 36 is an outlier. So we do have to include that in our check, outliers, and I did mention in video 1 we would do that. All right, second plot is what I care about for now, for the normal. To see if I have normal, I want my dots to be roughly scattered around this theoretical normal line. In my data, my residuals, as you notice, it says residuals, are roughly scattered, except for, again, this point and maybe these other 2 points. But this point, in general, seems to be causing us an issue. So overall, normality looks good, except for 1 point, maybe 2 others, that need to be investigated. There are other plots. I'm not so worried about those. So I'm going to hashtag normal looks good, except 1 point might be an issue. We'll have to further discuss that. All right, let's go back now and talk about independence. So if I'm going to do the independence check, I'm going to need to run the Durbin-Watson. See, the Durbin-Watson is an independence check. It's going to look to see if there's what is known as autocorrelation, which means there's no independence. So I really want to look at independence, and I would do this with the DW test, the Durbin-Watson test, and this looks for correlation, which means we do not have independence. So how does one run the Durbin-Watson test? Well, first of all, you need to install a very specific package called the CAR package. I'm going to comment because I already did it. So you would install the packages, and you would type, just like I have, the CAR package. That would be the package you would install. And then remember or recall, even after you've installed a package, you have to activate it in your menu screen. So you run the library. So if you run install packages CAR in library CAR, you will have the Durbin-Watson test. So now that we've run these, if I just start typing Durbin, the Durbin-Watson test comes up. The Durbin-Watson test, again, I'll leave you to look up the details of the Durbin-Watson test. But in Rstudio, it's really quickly to run, just as you see, Durbin-Watson test on my linear model, and boom, out pops out my values. And so in order to understand this test, you have to understand p-values and what they mean. So our p-value here is 0.268, and that is not significant. What that means is typically alpha is 10%, 5%, 1%. This p-value is above 10%, 5%, and 1%. So this p-value is not significant. What does that mean? That means I do not reject H naught. So to understand if that's important or not, you have to look up the hypothesis test. So in this case, when you do not reject, you actually are okay. So in this case, in this example, if we do not reject, we are good. What that means is we have no autocorrelation. You always have to, this is very important to me, you always have to read the hypothesis test for each test you run. If you don't do that, you'll have no clue what the p-value means. Our p-value in this case, 0.268, means we do not reject. Well, what the heck am I rejecting or not rejecting? Well, you're always rejecting or not rejecting H naught. That's great, but what the heck is H naught in this example? Well, you have to know what H naught is. In this example, H naught is we have no autocorrelation. H1, the alternative, would mean we do have autocorrelation. So we are lucky in this case that we do not reject. That means we do not have autocorrelation, and that means the independence is verified. Yay! So what we have just done is run all of our tests. We've run the linearity, the equivariance quickly by plotting our residuals versus our predicted, and we ran our independence by the Durbin-Watson test, and we ran our normality by looking at the plot of the model and finding the normal probability plot and noticing, for the most part, except for one dot, we don't have any issues. So overall, the residual analysis is really good. Now, I did notice that one dot, and in fact, I'm curious, are there any influential points, potential outliers? So I'd like to have an analysis on that before we finish. And so to do that, you would run Cook's distance. There are many ways for checking out outliers. For us, or for me, I like to use Cook's distance. So how does one use Cook's distance in Rstudio? Well, what happens is you first of all call it Cook1, and what you do is you ask Cook's distance, you ask this command line to find all the Cook's distances for the dots on your regression equation. And then we can plot the Cook's distances. And so what we have here is we have how far each one of these dots are away from the predicted. Really what Cook's distance is tracking is how far each one of these dots are away from the predicted line and which ones are too far away, which ones are too far away from the prediction lines. And what I have here is, for the most part, anything close to 0, these dots are really good. This dot maybe, and this dot looks highly suspected. But the problem is, unless you have a bound on Cook's distance, this really isn't helpful in this dot. This is potentially an influential point, but how do we know it? So what you have to check is your theory. You have to check your stats book on what does it mean to be a cutoff for the Cook's distance. The good news, I know that cutoff. And what you have to understand is these Cook's distances, they follow the F distribution. And since they follow the F distribution, to find the cutoff, we'd use the QF function, and we use a probability of 0.5. And you have to understand the degrees of freedom of the numerator of the F distribution. And in this case, the numerator's degrees of freedom would be k plus 1, where k is the number of independent variables. In this case, our number of independent variables, x's, is 1, so 1 plus 1 is 2. We also need to know our degrees for our denominator. Our degree for our denominator would be n minus k minus 1. N would be the total number of variables in your set. And as you could see, our total number of variables in our set is 36. And so we would do 36 minus k, so that's 35 minus another 1, so that'd be 34 is our degrees of freedom. And then we typically do lower tail is false when you're doing the QF, the quantile function for the F distribution. We get an answer, and that cutoff would be 0.707. So I imagine a line drawn right around 0.707, that if anything's under this line of 0.707, they are not, according to Cook's distance, a outlier or influential point. So all of these are not. This guy is clearly an outlier. And so hashtag, we do have one outlier / influential point. So the question is, what do you do with it? Well, that's up to the investigator. If you keep it in, you keep it in. If you want to do what I like to do, a thorough investigation, you take it out and rerun everything we've done in part 1 and part 2 of the videos, and then put them together and compare and contrast them in a very full, thorough investigation. But then again, that is up to you. I thank you for watching our first example. Look forward to seeing other examples on my site. Thank you, guys.